Hello everyone and welcome to the coronavirus edition of the 9th exercise from our signal theory class. In this exercise, just as in the lecture, we will practice the Z-transform. Here I have a simple discrete time filter, a discrete time system, and I would like to find out what is its transfer function, frequency characteristic, impulse response, and what is the output when at the input I have the unit step. By the way, the response to the unit step is called the step response. First, I need to write down the difference equation of this system. Then I need to take the Z-transform. This signal will become this Z image, this signal will become this Z image, and because of this time delay I will have this multiplication by Z to the minus 1. This signal will become this Z image and this signal will become this Z image, and again because of this time delay I will have this multiplication by Z to the minus 1. Now on the left hand side I will extract y of z, and on the right hand side I will extract x of z. That will give me this. Here I will divide by this polynomial, which will give me this. And here I have that the z image of the output signal is the z image of the input signal multiplied by this function of z, which we call the transfer function. So this is my transfer function, and when I want to get the frequency characteristic, I will substitute e to the j omega for z. When I substitute, I will get this. This is my frequency characteristic, which I could take to MATLAB and plot, and then figure out what type of filter this system is. If I do not want to plot this in MATLAB and I just want to sketch it approximately, I can use zeros and poles of this transfer function to do it. To get the zeros and poles of this transfer function, it is a good idea to put it in the form where I have positive powers of z. So in this case I need to multiply both numerator and denominator by z to the power of 1, which will give me this. And from here I can read that this transfer function has 0 at minus 1 because minus 1 is the root of this polynomial. When I substitute minus 1 here, I will get that this transfer function is 0. And this transfer function has pole at z is equal 1 over 2 because 1 over 2 is the root of this polynomial. When I substitute 1 over 2 here, this transfer function will be infinity. When I plot these zeros and poles into the complex plane, I will get this. This is my pole, this is my zero. Now the magnitude of the transfer function will have a big hill around this pole, and the magnitude of the transfer function will have a valley around this zero. Now, if I want to get the amplitude frequency characteristic, I need to trace the value of the magnitude of the transfer function above this unit circle. So I will start here. This point corresponds to the normalized frequency equal to 0, and then I go down the hill, down the hill, down the hill, down the hill. This point corresponds to the normalized frequency equal to pi over 2. Now I continue. I go down the valley, and all the way to this 0. And this point corresponds to the normalized frequency equal to pi. And I continue. I go up the valley, up the valley, up the hill, and I will come back where I started. So when I trace the magnitude of the transfer function above this unit circle, I will get this. So this is an approximate sketch of the amplitude frequency characteristic of my system. And from here I can see that my system is actually a low-pass filter. If you actually went into trouble of plotting the magnitude of the transfer function in MATLAB, you would get these 3D plots. So this hill is created by this pole, and this valley is created by this 0. And this red line gives you the values of the magnitude of the transfer function above the unit circle. Here I have removed the plot of the magnitude of the transfer function outside the unit circle, so you can see it a little bit better. This is the unit circle, and these are the values of the magnitude of the transfer function above the unit circle. So this is my amplitude frequency characteristic. And here you have it plotted. you can see that my sketch is not exactly the true amplitude frequency characteristic, but even from this sketch I was able to judge that this system is a low-pass filter. Now, what about this impulse response? If I want to find what is the impulse response at the input, I need to put the Dirac delta pulse, because then at the output I will get the impulse response. So in the Z domain, the Z image of the output will be the Z image of the input times the transfer function. In this case, the Z image of the input will be equal to 1, so the Z image of the output will be just the transfer function. And this is my transfer function. Now I need to break this transfer function to partial fractions to be able to do the inverse Z transform. As on the lecture, I will work with this Z to the minus 1 as if it was just a single variable. If it confuses you, you can write just some Q instead of Z to the minus 1 and work with that. Now, if I did a regular partial fraction decomposition, this would give me a little bit of trouble because here I have the same order of the numerator as is the order of the denominator. So in that regular partial fraction decomposition, I would need to divide the numerator by the denominator. But with the Z transform, you can actually avoid this and you can do the following trick. You can divide this part of the numerator by the denominator and this part of the numerator by the denominator. So you will get this and this. Now, using this formula, you can see that this partial fraction actually corresponds to this when this A is 1 over 2. So this is the Z image of this geometric series. In this case, this fraction is actually the same as this fraction, except it is multiplied by Z to the minus 1. And in the Z transform, multiplication by Z to the minus 1 in the Z domain actually causes this time shift in the time domain. So this fraction is actually the Z transform of the same geometric series as this fraction, except the geometric series has to be time shifted by 1. So when I put this together, this is the output of my system when at the input is the Dirac delta pulse. So this is the impulse response of my system. Now this problem C, what is the step response of my system? In the Z domain, I will still have that the Z image of the output is the Z image of the input multiplied by the transfer function. So I need to substitute. This is my transfer function, and then I need to substitute for the Z image of the input. The Z image of the unit step is this. So this is the Z image of my output. To get the output in the time domain, I will need to take the inverse Z transform of this. For that, I will need to break it to partial fractions. This I can break to these partial fractions, and using the cover-up method, I can find that these constants A and B are actually -3 and 4. So this is the decomposition to partial fractions. And now again, using this formula, I can see that this is the Z image of this geometric series, and this is the Z image of the unit step. So when I put this together, this will be the response of my system to the unit step. This will be my step response. Here I have another example, but this time I have a second order system. My question is, what is the frequency characteristic and what is the impulse response? So first, I will write down the difference equation of this system. Then I will apply the Z transform. That will give me this. Then on the left hand side I will extract y of z, and on the right hand side I will extract x of z. And I will divide by this polynomial, which will give me this form. And from here I can read that this is my transfer function. This is my transfer function. Now when I substitute e to the j omega for z, I will get this frequency characteristic. If I want to sketch this frequency characteristic, I need to find where the zeros and poles of the transfer function are. To get the zeros and poles of the transfer function, it is best to put the transfer function in the form where I have positive powers of z. In this case, I need to multiply both the numerator and the denominator by z to the power of 2. When I do that, I will get the transfer function in this form. And from here I can read that the roots of this numerator are plus minus 1, which means that this transfer function has two zeros. One zero is at plus 1, the other is at minus 1. And from here I can read that the roots of the denominator are plus minus 1 over 2 times j. That means that this transfer function has two poles. One pole is at plus 1 over 2 times j, the other pole is at minus 1 over 2 times j. When I take these poles and zeros and I plot them into the complex plane, I will get this. These will be the poles and these will be the zeros. Now the magnitude of the transfer function will have big hills around these poles, and it will have valleys around these zeros. If I want to get the amplitude frequency characteristic, I need to trace the magnitude of the transfer function above this unit circle. So I will start here and I will go up the valley, up the valley, up the hill to the top of this hill, and that corresponds to this part of the amplitude frequency characteristic. Then I go down the hill, all the way to the bottom of this valley, and that corresponds to this part of the amplitude frequency characteristic. And then I will go up the valley, this will be the highest point of the hill, and then I go down the hill, all the way to this zero. And that corresponds to this part of the amplitude frequency characteristic. If you want to know what the magnitude of the transfer function looks like when you plot it in MATLAB, this is what it looks like. You can see these two big hills that correspond to these two poles, and you can see this valley and this valley that corresponds to this zero and this zero, and this red line are the values of the magnitude of the transfer function above the unit circle. Here you can see it with the plot of the magnitude of the transfer function outside of the unit circle removed. So this is the unit circle, and this red line corresponds to the amplitude frequency characteristic. And this is the actual plot of the amplitude frequency characteristic. Now, what about this impulse response? If I want to get the impulse response at the output of my system, at the input I need to feed the Dirac delta pulse. In that case, the z image of the output is equal to the transfer function, this transfer function. I will proceed with negative powers of z. If that bothers you, you can replace z to the minus 1 by some constant q and work with that. If you do, you are going to end up with q squared here and q squared here. Now I need to solve the problem that the order of the numerator is the same as the order of the denominator. I can do the same thing that I did in the previous example. I can divide this part of the numerator by the denominator, and that will give me this. And I can divide this part of the numerator by the denominator, and that will give me this. And now I could proceed to break these expressions into partial fractions and then take the inverse z transform. However, in this case, this approach would lead to longer computation and I would get an uglier result. So instead, I will use approach that we used with the Laplace transform. There we used a trick which was equivalent to polynomial long division. We altered this fraction so that a part of the numerator was the same as is the denominator, and then when we divided the numerator by the denominator, we actually got a rational polynomial function which had the order of the numerator less than was the order of the denominator. Specifically, this is what we need to do. I can multiply both this fraction and the denominator by -4, and that will give me this. Now, in the numerator, I can add and subtract this -4, And now I can divide this part of the numerator by the denominator, and that will give me this number 1. And I can divide the rest of the numerator by the denominator, and that will give me this. And here you can see that thanks to this approach, I ended up with a rational polynomial function which has the order of the numerator less than the order of the denominator. And now I can proceed to break this into partial fractions. Before I do that, I will first multiply this minus 4 with this partial fraction and this constant, and that will give me this. Now I will factor this polynomial into the product of these two first-order polynomials, and this rational polynomial function I can break to these partial fractions. These constants I will get by applying the cover-up method to this rational polynomial function. Now to take the inverse z transform of these partial fractions, I need to use this formula. So I need to alter these partial fractions into this form. To do that, I need to divide both the numerator and the denominator of this partial fraction by 2j, which will give me this. In this case, I need to divide both the numerator and the denominator by minus 2j. That will give me this. And now using this formula, I can write that the inverse z transform of this partial fraction is this, and the inverse z transform of this partial fraction is this. The inverse z transform of a constant is just a Dirac delta pulse multiplied by that constant. So this is the impulse response of my system. Now I will show you how you can simplify it a little bit. You can take this geometric series and break it into the product of these two geometric series. And you can take this geometric series and break it into the product of these two geometric series. And you can also write this j as e to the j pi over 2, and you can write this minus j as e to the minus j pi over 2. Then you can take this 5 over 2 and this 5 over 2 and extract it in front of a bracket. Then you can take this geometric series and this geometric series and to extract it in front of the bracket. In the bracket, I'm left with this expression to the power of n, which is this, and this expression to the power of n, which is this. So this expression and this expression I can write like this. And of course I will just copy this Dirac delta pulse. Now I can combine these two exponentials and they will give me a cosine. So I can simplify that impulse response into this form. So this is the impulse response of my system. In this example, I have an FIR filter, and I would like to know what is the transfer function, frequency characteristic, impulse response, and what is the output when at the input I have the unit step. I will start by writing down the difference equation of this system, which is this. Now I will need to take the z transform of this equation. That will give me this. Now on the right hand side, I need to extract this x of z, and that will give me this. And from here I can read that this is the transfer function of my system. For FIR filters that have only this feed-forward path, the transfer function is always in this form of polynomial of negative powers of z. If you want to get this transfer function into the form where you have only positive powers of z, you need to both multiply and divide this transfer function by z to the power of 2. When you do that, you will get this. And because for FIR filter the transfer function in the negative powers of z was in the form of this polynomial, the transfer function with positive powers of z will always have this form where you have the polynomial of positive powers of z and then you just divide by some power of z. This power will be the same as the highest power in the numerator. Now I can simplify this transfer function a little bit by noting that this can be written as this. So I can write my transfer function in this form. Now, when I substitute e to the j omega for z, I will turn this transfer function into the frequency characteristic. And if I want to sketch this frequency characteristic, I need to find where the zeros and poles of my transfer function are. So this transfer function will have a 0 at -1, and because this is squared, we say that it is so-called double zero. Essentially, this transfer function has two zeros at -1. And this transfer function will have a pole at 0, and because this is squared, we say that it is so-called double pole. Essentially, the transfer function has two poles at 0. Now, this is quite typical for FIR filters. FIR filters have their transfer function in the form where you have only some power of z in the denominator. So they will always have their poles at 0. FIR filters always have their poles at 0. Now I can take these zeros and poles and plot them into the complex plane. This is my double pole at 0 and this is my double zero at -1. And the magnitude of the transfer function will have a big hill around this double pole and it will have a valley around this zero. And if I want to get the amplitude frequency characteristic, I will need to trace the magnitude of the transfer function above this unit circle. So I will start here, and now I can see that I will go down the hill, down the valley, all the way to the zero. And that is what I draw into my sketch of the amplitude frequency characteristic. Then from here I go up the valley, all the way to this highest side of this hill. And that is what I have in the sketch of my amplitude frequency characteristic. The exact magnitude of the transfer function and the amplitude frequency characteristic look like this. This is the magnitude of the transfer function. And here you can see this hill created by this double pole, and here you can see the valley created by this double zero. And this is the exact plot of the amplitude frequency characteristic. Now the impulse response. So again, to get the impulse response, I need to feed the Dirac delta pulse into my system, and when I do, the z image of the output will be equal to the transfer function, which in this case has this form. Now I need to take the inverse z transform of this to get the impulse response in the time domain, and that is very easy. This is just a constant, so the inverse z transform is the Dirac delta pulse. This is just a constant multiplied by z to the -2, so the inverse z transform is the constant multiplied by the Dirac delta pulse, but because of this z to the -1, I will have this time shift here. And this is again just a constant multiplied by z to the -2, and that will give me this time-shifted Dirac delta pulse. Now the step response, the response to the unit step. In this case, the z image of the output will be given as the transfer function times the z image of the input. This is the transfer function, and the z image of the unit step is this. Now I need to take the inverse z transform of this expression, and in this case the easiest way to do this is to divide these elements of the numerator separately and to write it like this. And now this is the z image of the unit step, so when I do the inverse z transform I will write unit step. This is the z image of a unit step but multiplied by z to the -1 and this constant. So when I do the inverse z transform of this fraction, I will get the constant times the unit step and I will get the time shift. And here I have the same thing, except I have the time shift by 2, so the inverse z transform of this expression is this. In this example, I have this simple IIR filter, IIR system. I would like to know its frequency characteristic, impulse response, and I would like to know what is the output of this system when this is the input. As in the previous examples, I need to write down the difference equation of this filter. Then I need to take the z transform and alter this equation into this form where I can read the transfer function. So this is my transfer function, and when I substitute e to the j omega for z, I will turn this transfer function into the frequency characteristic. If I want to sketch this frequency characteristic, I need to find the zeros and poles of this transfer function. For that, it is best to have it in the form where I have positive powers of z. So in this case, I need to multiply both the numerator and the denominator by z. When I do that, I will get this. And from this transfer function, I can read that this transfer function has 0 at 0, and this transfer function has pole at 0.5. When I plot this 0 and this pole into the complex plane, I will get this. This is my pole, this is my 0. The magnitude of the transfer function will have a big hill around this pole, and it will have a valley around this 0. When I want to get the amplitude frequency characteristic, I need to trace the magnitude of the transfer function above this circle. So I will start here, and I will go down the hill. Then I will arrive to this lowest point, and then I will start to climb, and I will go up the hill, back where I started. So this will be the shape of my amplitude frequency characteristic. Now, if you bothered to plot this in 3D, this is what it would look like. This hill is created by this pole, and this valley is created by this 0. And this red line are the values of the magnitude of the transfer function above the unit circle. And they correspond to my amplitude frequency characteristic. Okay, now the impulse response. From the previous examples and from the lecture, you know that the impulse response is the inverse z transform of the transfer function. So I need to compute the inverse z transform of this transfer function, which is very easy, that is this. So this is the impulse response of this IIR filter. Now, what is the output of my filter when this is the input? Now, you could take the z transform of this cosine, multiply it by the transfer function, and then compute the inverse z transform. But the z transform of a cosine is rather ugly, so if you did it this way, you would be pulling your hair when you try to do the inverse z transform. So instead of tackling the entire cosine at once, it is actually more convenient to break it into smaller steps. What do I mean? You can break this cosine into two complex exponentials, and you can do the computation exponential by exponential. So first, I will start by computing the output of this filter when the input is just this complex exponential. I first need to compute the z transform of this complex exponential, and to do that I can rewrite this complex exponential as this geometric series. And I know what the z transform of a geometric series is. That is this. Now the output for this input will be the z transform of this input times the transfer function. Here I have it substituted. This is the transfer function, this is the z transform of this input. And here I can break this expression into partial fractions. Again, I will work with this z to the minus 1 as if it was a single variable. The constant in the numerator of this partial fraction, I can just simply compute by using the cover-up method. The root of this polynomial is z to the minus 1 equal to 2, and I cover this up and substitute the number 2 here. That will give me this. Now, what about this constant in the numerator of this partial fraction? It goes like this. this expression has the root, this expression is 0 when z to the minus 1 is equal to e to the minus j omega. I have it here so that it is easier to follow. When I substitute e to the minus j omega for z to the minus 1, this expression will become this, and that is equal to 0. So this is the root of this expression. So now I cover this up and I will substitute this root into this expression. And this expression happens to be the transfer function of my system. So I will be substituting this into the transfer function. And it also happens that this is equivalent to this. So instead of this, I can make the substitution that e to the j omega is equal to z. So I will be making this substitution into the transfer function. And that will give me this. And this also happens to be the frequency characteristic of my system. So the constant in the numerator of this partial fraction will be given by the frequency characteristic at the normalized frequency omega, at this normalized frequency omega. So this is how I can break this expression into these two partial fractions. And now taking the inverse z transform is quite easy. All I need to use is this formula. This partial fraction has this form, this is just a constant, so the inverse z transform of this is going to be this geometric series multiplied by this constant, that is this constant. And the same goes for this partial fraction. This partial fraction actually has this form, this is just a constant for given omega, so this partial fraction will have inverse z transform in the form of this geometric series. And here I multiply by this constant by this constant. This expression I can simplify it a little bit and I can write it in this form. So this will be the output of my system when the input is this complex exponential. Now what about this cosine? This cosine I can break into these two complex exponentials. And now I already know that when I feed the system this exponential, I will get this output signal. So when I feed the system 3 times this exponential, I will get this output except multiplied by 3. And that is what I have here. And when I feed the system this exponential, I will get the same result as for this exponential, except my frequency omega will be negative. So I will get this, which is the same as this, except now my frequency omega is negative. So this will be the output of my system when this is the input. But this form is rather ugly and I can simplify it. I can put together this term and this term, which will give me this, and here I can actually combine these two fractions. When I sweat it out, I can actually show that these two fractions are equal to this fraction. Now I can combine this term and this term, which will give me this. On lecture 7, I showed you that the combination of these two complex exponentials can be written in this form, where this is the amplitude frequency characteristic and this is the phase frequency characteristic. So you can use these simplifications and you can write the output of your system in this form. And in this form you can actually recognize two parts, the transient and the steady state. This transient is actually just a geometric series which will approach 0 as this n increases. So this transient can be noticeable at the initial part of the response, but then as n increases it will become negligible. And when this transient becomes negligible, only this steady state will remain. And this steady state is actually the same cosine as is the cosine at the input, except it is scaled in amplitude and shifted in phase. The scaling in amplitude is provided by the magnitude of the frequency characteristic, and the shift in phase is given by the phase of the frequency characteristic. So this is how you can use the Z-transform to compute the output of your system if the input of your system is a cosine or a sine. If you do not care about this transient and you are interested only in this steady state, then you do not even have to do this computation. All you need to do is to compute the transfer function, the frequency characteristic, and then use the magnitude of the frequency characteristic and the phase of the frequency characteristic and scale this input cosine or a sine in amplitude and shift it in phase, and that will immediately give you the steady state output of your system when this is the input. On this and a couple of next slides, I have a few simple filters that you should be aware of. This filter is called the Integrator, and it has the same structure as the filter from the previous example, except this time I have this general coefficient A1. This is the difference equation of this filter, and if you wanted to implement this filter in MATLAB, you would need to use these A and B coefficients. This is the transfer function of this filter, and this transfer function has 1, 0 at 0, and it has one pole at minus a sub 1. If I set this coefficient a1 to minus 0.5, I will get the same case as I had in the previous example. These would be the positions of the 0 and the pole. This would be the plot of the magnitude of the transfer function, and this would be the amplitude frequency characteristic. Now, if I change this coefficient a1 so that it will get closer to minus 1, that will cause this pole to move closer to the unit circle. When this pole moves closer to the unit circle, the hill created by this pole will pull the amplitude frequency characteristic higher up than in the previous case, which will cause the amplitude frequency characteristic to be more selective for lower frequencies. If I overdo it and I set the coefficient a1 to a value which is less than 1, this pole will get outside of the unit circle and the system will be unstable. When the system or a filter is unstable, it does not even have the frequency characteristic. In this case, the frequency characteristic does not exist. Now, if I set the coefficient a1 to a positive value, this pole will move to the left-hand side of the complex plane. In this case, the plot of the magnitude of the transfer function will look like this, and this will be your amplitude frequency characteristic. So if this pole moves to the left-hand side of the complex plane, you will end up with a high-pass filter. So this filter can be either low pass or high pass depending on the value of this coefficient a1. This filter is called the moving average because essentially what it does is that it computes the average of the last m samples. So this is the difference equation of this filter, and if you wanted to implement it in MATLAB, you would use these a and b coefficients. This is the transfer function of the filter, and this is a finite sum of a geometric series which you can write like this. And here you can multiply both the numerator and the denominator by z to the power of m, which will give you this. Here the roots of the polynomial in the numerator are these. The denominator has a single root at 1 and a multiple root at 0. The multiplicity of the root at 0 is m minus 1. Now, these roots, these complex values, are evenly spread around the unit circle. This root would actually be here at a position of z is equal to 1, but because the denominator also has the root at z is equal to 1, this root and this root will cancel each other out, and only these will be the zeros of my filter and this will be the pole of my filter. The final shape of the frequency characteristic will depend on how many values I average. If I average 4 values, these will be the zeros and poles of my transfer function. This will be the plot of the magnitude of the transfer function, and consequently the amplitude frequency characteristic will have this shape. If I average, for example, 8 values, these will be the zeros of my transfer function, this will be the multiple pole of my transfer function, this will be the plot of the amplitude of the transfer function, and this will be the amplitude frequency characteristic. You can see that the moving average implements a low-pass filter, and I can make that filter more selective for lower frequencies by increasing the number of values that I average. Now, this filter is called the comb filter, and essentially what it does is that it computes the difference between the input sample and the input sample delayed by m samples. If you wanted to implement this comb filter in MATLAB, you would need to use these a and b coefficients. This is the transfer function of your filter, and you can also write it like this. This numerator will give you these m zeros, and this denominator will give you pole at 0 with multiplicity m. Now these zeros will be evenly spread around the unit circle, and this pole will sit at the origin. This is always the case for FIR filters. For FIR filters, we always have a multiple pole at 0. Now the specific shape of the transfer function and the frequency characteristic will depend on this delay m. If that delay m is 1, I will have 1 0 and 1 pole. This will be the shape of the magnitude of the transfer function, and this will be the amplitude frequency characteristic. You can see that in this case, this filter will be a high-pass filter. If this delay is 4, I will have 4 zeros and 4 poles. This will be the shape of the magnitude of the transfer function, and this will be my amplitude frequency characteristic. If this delay is 8, these will be my zeros, and these will be my poles. This will be the shape of the magnitude of the transfer function, and this will be the amplitude frequency characteristic. And you can see that for higher values of this m, for this delay, the shape of the frequency characteristic resembles a comb. And that is why we call this filter the comb filter.